drain. And there is a semiconducting layer as well as a dielectric layer. So for the first there will be at the bottom there is a gate, and for gate we can use either polymer or either any metal.
Just see. Sound is not coming. Huh?
We can heat our silicon wafers and it will thermally corrode silicon dioxide. And when we are having IDO coated PET or pen, then that time we can use PMMA or other dielectric materials. After that, we can fabricate our semiconducting layer using spin coating technique. And over that, we can have our source and drain terminals. So for source and drain, we can use those metals, like we can use either gold, silver, platinum, or palladium, which are having good work functions, which are having high work functions. So this OFET devices, they can be fabricated in 4 ways. We can have the first one like a top contact and bottom gate configuration. So in the top contact bottom gate, we are having the gate electrode at the bottom of the substrate, and we are having the source and drain over the semiconducting layers. In the bottom gate, bottom contact configuration, we are having the gate at the bottom, but now the source and drain electrodes are placed under the semiconducting layers. Then we are having the top gate top contact configurations and top gate bottom contact configurations. So when we are having the top gate, that means like gate electrode will be placed over the substrate, and source and drain electrodes will be over the semiconducting layers. Likewise, we will be having top gate and bottom contact devices. So over that, this top contact and bottom gate this top contact and bottom gate architect were always preferred because they will give a high contact area between the electrodes and the semiconducting layers. So for the working of this OFET devices, here is the basic diagram. This we are having substrate, then we are having gate electrode, we are having dielectric, we are having our active semiconducting layer, and obviously source and drain. So for the amount of current that flows from the source and drain, it all depends upon how much voltage we are applying to the gate. So when one more thing is there, I have to tell you what is the threshold voltage. So the minimum voltage that will apply between the gate and the source, that will cause this channel electron and channel to form between the source and drain, that is called threshold voltage. So when we are applying a positive voltage between the when we are applying a positive voltage that is higher than the threshold voltage between the gate and source, we will be getting a this N channel here, N channel here. So when we are applying a negative voltage between the drain and source, we will be getting the flow of electron from source to drain. So as the amount of gate drain source current, it comes to where this drain source current reaches its maximum value. So here this is the working of an N-type OFET, and here this is in this side we are having the working of a P-type OFET. So with this data we can plot two curves, output curves and transfer curves. Output curves is between the drain source voltage and drain source current, and transfer curves will also be there. From this, what will be the this efficiency of this OFA devices, like whatever we have plotted, we can check its efficiency by calculating their carrier mobility, their current on-off ratio, and threshold voltage. So if we have to improve the overall performance of any OFA device, we need to improve its semiconducting layer quality. So we can improve the performance of any semiconducting layer if we introduce any pi conjugated spaces. For that we can use ethylene, ethine, or any pi conjugated molecules like phenyl, thiophenes, biphenyl, and others. With the introduction of these pi conjugated spacers, it will extend the pi conjugation and eliminate the steric repulsion. It will give a planar configuration to the molecule and it will assist in the self assembly. We can also tailor make our molecules, like we can use different type of architect. So here in the first example, we are having donor receptor donor type of architect, and in the second one we are having donor receptor donor pi linker acceptor pi linker type of architect. So in this one, the benzocarbazole acted as a donor molecule, and we are having DPP molecule as our receptor, and then again followed by a donor moiety. So here we are having any aryl group which will act as our donor. Then they have used acetylene as our pi linkers, then our receptor moieties, again pi linkers, and then donors. So I have worked on quinolines. So it's a versatile molecule. So the reason to choose quinoline was because it's a fusing aromatic compound. It is having sp nitrogen atom, which was supposed to increase its electron efficiency, and it will result in a widened band gap. It's a planar molecule, thus it can result in a better charge delocalization. And with bottom-up molecular engineering, we can tune its electronic properties as well. So during my that PhD work, I have worked on this quinoline based molecule, and here in the first part of the work, we have taken 4-carboxylate quinoline as our core moiety. Then at the ends, we are having substituted phenyl group as our pi end caps. So here we have introduced 4-carboxylate. We have introduced this ester group at the fourth position to improve the overall solubility of the compounds. In the later part, we have introduced ethynyl as a pi conjugated spacers, which were supposed to give it rigidity to this whole compounds and assist in self-assembly. And later we have used acetylene as well as phenyl group as a pi conjugated spacer. And in the further part, we have explored the acetylene by this triphenyl group and this type of architect and this type of architect and for the OFIT. So in this work, we have synthesized various compounds following this architect. Their structure property relationship were also explored. The OFIT devices, we have made the OFIT devices inside the lab, and we have studied their OFIT characteristic as well. So in the first part, we have used this donor acceptor donor linkage type of architect and donor type of architect molecule. So for the synthesis of these molecules, we have carried out Fitzinger reaction between the 5-bromo icyatine and substituted acetophenone in alkaline condition to give compound 1. So here the compound 1 then underwent esterification. The reason to do the esterification is just to improve the overall solubility of the compound. And this compound 2 then underwent Suzuki coupling reaction to give the final compounds in good yield. These are the final compound that was synthesized. So here we are having simple phenyl as our end caps. Then in compound 3B we are having 4-methoxyphenyl and this simple phenyl as at the 6th position of the quinoline core. Then we are having 4-methoxyphenyl group as our end caps. Likewise, we are having in compound 3D, we are having 4-methoxyphenyl and chlorophenyl as our pi end caps. Then in compound 3E, we are having 4-methoxy and biphenyl at the 6th position. And in compound 3F, we have this 4-methoxyphenyl and at the 2nd position and thiophene at the 6th position. So all these compounds were synthesized and were confirmed with NMR and HRMS, and the structure property relationship were explored. So this is the The photophysical properties were determined by recording their absorption and emission spectra. So, in the absorption spectra, we have observed a sharp band in the high energy region. This sharp band corresponds to pi to pi star transition, and then we have a lower energy band which corresponds to n to pi star transition. So here the highest absorption maximum was observed for compound 3F, which is having 4-methoxyphenyl and thiophenyl as its end terminal. And their emission spectra were also recorded, and we have obtained emission maxima. The highest emission maximum here, their emission spectra was also recorded, and from their absorption emission maximum, we have calculated the Stokes shift values. The highest Stokes shift values here was observed for compound 3C, that is this 4-methoxyphenyl substituted compound. So for these compounds, their electrochemical properties like their homolume levels were calculated. To do that, we have recorded their we have carried out cyclic voltammetric studies, and we have plotted the cyclic voltograms. So for these compounds, we have observed peak only in the negative potential. So from their negative potential values, we have calculated the LUMO energy levels, and from there we have calculated the HOMO and energy gap band gap. So for all these compounds, their LUMO energy levels lies in the range of -2.92 to -2.95, and HOMO energy levels were in the range of -6.12 to -6.35. So because of these HOMO and LUMO energy levels, they have the tendency that they can act as a p-type materials. So here for the dimethoxy substituted compound, we got the highest LUMO and HOMO energy level. So obviously for the durability and for the stability of any organic compound, their thermal stability is really important. And for that, we have recorded their DSC thermo. We have done a differential scanning calorimetry technique. So to determine the melting point. Here, all these compounds were thermally stable with melting point higher than 151 degrees Celsius. The compound 3E with 4-methoxyphenyl group as the N group resulted in a highest melting point. So when these compounds were fabricated and the surface morphological studies were done using scanning electron microscope techniques, so the presence here, with the presence of different N groups resulted in versatile morphology. So as we can see, we got a flower-like arrangement. Then some this rectangular rods were also observed. So we were able to crystallize most of the compounds, and this is a single crystal XRD analysis of those compounds. We have recorded their GXRD patterns as well, and the sharp peaks do represent that the films formed were polycrystalline, and they do have some self-assembly in them. So for these compounds, we have fabricated OFET devices. We have used silicon wafer as our substrate. Then we have thermally cloned silicon dioxide as our dielectric layer. Then we have spin coated our active layers using spin coater with a static spin coating technique. And then we were having the source and drain terminals. Here, their transistor curves were plotted, and this is the characteristic transistor curve for compound 3C. So the highest hole mobility here was observed for dimethoxy substituted compound 3C with the hole mobility of 0.0032 centimeter square per volt per second. It does show a on-off ratio of 10 raised to power 4 with a threshold voltage of -29 volt. So all these experimental data were supported by our computation analysis. So this is the electron density distribution of these compounds, the electron density distribution here suggests that HOMO and LUMO levels were extensively delocalized, uh, which does support their whole mobility. Their molecular packing studies were also done, and their interacting hopping distances or interactive distance values were calculated. The highest whole mobility in compound C, that is methoxy and cat compounds, were also supported by these values as they got the lowest hopping distance. So in the second part, we are having this d pi and d pi.
Presentation is not available. We cannot see. I cannot see the presentation.
Yeah, it's visible. Presentation is visible. It's coming. Maybe please check your system, sir.
Okay, okay.
Yeah, it's visible. Slides are visible. Yeah.
So whether I'm audible.
You are audible and the slides are visible. Yes.
Okay. So in the second part of the work, we have this pi extended QLNine for solution processable ambipolar organic field effect transistor. So here we have used donor D pi AD and D pi A type of architect. So we have again we have taken 4-carboxylate QLNine as a core moiety. Oh, sorry. Yeah, again we have taken 4-carboxylate as our core moiety. Then we are having a substituted phenyl group as our donor moieties, and here we have introduced acetylene as a pi linkers. So again, for the synthesis of this compound, we have carried Fitzinger reaction, then followed by esterification, and the compound 2 here then underwent Sono-Kushida coupling reaction to give the compound 3. So this is a structural representation of all the synthesized compound. Here the compound 3A, 3B, and 3C are having simple phenyl group added second position, and we have changed the substituent here with the acetylene group. In compound 3D, 3E, and 3F, we are having 4-methoxy phenyl group as our end groups, and compound 3G2, 3G, 3H, and 3I are having 4-fluorophenyl group as our end groups. So for this compound, their photophysical analysis were done. We have recorded their absorption and emission spectra. So in the absorption spectra, we have observed a sharp peak from 250 to 300 nanometer, and a shoulder band from 300 to 350 nanometer, which corresponds to pi to pi star transition. Then a lower energy band from 350 to 400 nanometer, which corresponds to n to pi star transition. These compounds have also exhibited intermolecular charge transfer effect, and here the higher ICT effect were observed for compound 3D, 3E, and 3F. It might be because of their extended conjugation due to the presence of this 4-methoxyphenyl group. So from the emission spectra we have recorded we have calculated their Stokes shift values as well, and the highest Stokes shift values here were observed for compound 3B and 3H. So the reason for higher Stokes shift might be because of the reorganization of this molecule in the excited state. So for these compounds, we have observed peak in the negative as well as positive potential in cyclic voltograms. So we have calculated from onset oxidation potential, we does have calculated the HOMO energy levels, and from their onset reduction values, we have calculated their LUMO energy levels. The calculated band gap values were in accordance with the optical band gap that we have calculated from absorption onset values. So for these compounds, their HOMO energy level lies in the range of minus 5.21 to minus 5.85, and LUMO energy levels lies in the range of minus 2.98 to minus 3.87. So these compounds can be used as an ambipolar molecules because they have their HOMO and LUMO levels are in that range. So therefore, this compound, their thermal analysis for their stability and durability, their TG and DSC techniques analysis were done, and these compounds they are thermally stable. They are having their melting point was recorded as a sharp endothermic peak. So all these compounds are having melting point higher than 130 degrees Celsius, and their decomposition temperatures were higher than 321 degrees Celsius. So we have fabricated we have fabricated a device with bottom gate top contact configuration. So this is a characteristic transistor curve for compound 3 that 4-methoxyphenyl substituted compounds 3E, and from there we have calculated the hole as well as electron mobility. So for compound 3E, 3F and 3G, these three compounds have exhibited ambipolar transistor behavior, like they have shown hole mobility as well as electron mobility. The better results were observed for for 4-methoxyphenyl substituted compound 3E, where we have gotten a whole mobility of 0.1 centimeter square per volt per second, with a current on-off ratio of 10 raised to power 4 and a threshold voltage of minus 18. This compound also resulted in a whole electron mobility of 0.05 centimeters centimeter square per volt per second, with a current on-off ratio of 10 raised to power 3 and threshold voltage of 9. So we have obtained single crystal for all these compound except compound 3E, and the better result in compound 3F and 3G were supported by their less interactive distance well. So for surface morphology of this were again studied using scanning electron microscope technique. And here for compound 3A, 3B, and 3C, we have observed microbundles for compound 3E, 3D, 3E, and 3F, which are having 4-methoxyphenyl group as at the second position. They resulted in a flower-like morphology. And compound 3G, 3H, and 3I with 4 fluorophenyl group at its one terminal, they resulted in closely packed cuboids and these hexagonal structures. So for these compounds, their average grain size values were also calculated. So all the experimental data were supported by the computational. This is the 4-methoxyphenyl substituted compound. This is their electron density. This is their energy minimized structure. Here we can see that electron cloud is extensively delocalized over HOMO and LUMO energy levels. So this is the molecular packing that has been recorded for compound 3E and 3F. So for this compound, for compound 3F with 4-methoxyphenyl and this tertiary butyl phenyl group at the N terminal, it is having high volume. That means like the electron energy distribution is really good there, and which also resulted in low interatomic distances. So for the third part, we are having this. We have explored aryl and ethynyl spacer. Here we are having donor, pi linker, acceptor, then pi linker again, and donor type of architect. So for the synthesis of this compound, again Fritzinger reaction was carried out. Then we have done esterification. Then we have done our Sohn-Kushida coupling reactions. So these are the structural representation of the synthesized compounds. Here both at the terminals we are having the same end caps. So here in 3A we are having simple phenyl groups. In compound 3 we are having tertiary butyl phenyl group, and in compound C we are having 4-methoxyphenyl group. And in compound 3 we have explored thiophene, and then we are having this electron withdrawing 4-fluorophenyl group. And in compound 3 we are having cyano phenyl group at the end terminals. For these compounds, again, their photophysical studies were done. We have recorded their absorption and emission spectra. So in the absorption spectra, we have observed a band in there from. We have observed a band from 250 to 350. We have 250 to 280, and then 280 to 380 nanometer. 380 that corresponds to pi star transition, and then another band from 380 to 450 nanometer, which corresponds to N to pi star transition. So here the compound 3A with the phenyl as end caps, then compound 3C with 4-methoxyphenyl as end caps, and compound 3E with 4-fluorophenyl as end cap resulted in higher ICT effect. So when we are comparing these compounds with the previous set of molecules with only one pi linker, they did exhibit a red shift, which might be because of the extended conjugation with additional phenyl as a pi linker here. So in the absorption spectra, we have observed a broad emission band for the compound 3F with the this cyno functionalization. We have observed a blue shift in the absorption and emission spectra. So for these compounds, the cyclic voltammetric studies were done, and in the cyclic voltograms were recorded. And as we can see, these compounds resulted in peaks only in the negative potential. Thus, from their onset reduction values, their LUMO energy levels were calculated, and then from there we have calculated their HOMO and this band gap values. Here for these compounds, their LUMO energy levels were in the range of -2.95 to -3.13, and their HOMO energy levels were in the range of -5.75 to -6.18 electron volt. And for compound 3C, we are having both high HOMO and LUMO energy levels. And for compound 3F with this cynofunctionalization, we are having low HOMO and LUMO energy levels. So we have recorded the TGA, we have recorded this thermal gravimetric analysis, and we have DSC thermograms as well. So these compounds are thermally stable as they are having melting point higher than 204 degrees Celsius and decomposition temperature over 381 degrees Celsius. So when we are comparing this compound to the previous one, almost 94 degree increase in their melting point was observed, and their almost 100 degree increase in their decomposition temperature was observed. So their fabricated active layer for the morphology was determined using scanning electron microscope technique. And here we are having, with different functionality, we are having the versatile morphology here. So from there we have calculated their average grain size values as well. And so when we are looking at it, we can see like there is a uniform coverage, so which will facilitate their mobility values. We does obtain a single crystal for them, and this is the single crystal XRD studies. This is the PI XRD spectra that we have recorded for these compounds. So for these compounds, we have fabricated their OFET devices and recorded their transistor characteristic curves. So these compounds have exhibited nice hole mobility. Here the compound 3C with the 4-methoxyphenyl as our end terminal have resulted in the highest hole mobility. Here with the hole mobility of 1.39 centimeters square per volt per second, with a current on-off ratio of 10 raised to power 6 and a threshold voltage of -1. And their electron density distribution curve suggests that for these compounds, their HOMO and LUMO energy levels were extensively delocalized. Their molecular packing were also done, and from their molecular packing, we have calculated the hopping distance values, which is favoring compound 3C, which is 4-methoxyphenyl at the end terminal. They are having less hopping distance values. For the fourth part, we are having triaryl and ethynyl spacer functionalized quinolene. So for the synthesis of these compounds, we have carried out Fitzinger reaction followed by esterification. Then for the compound to underwent Sonneck-Fischer cross-coupling reaction, which then went to compound third, then underwent Suzuki coupling reaction with this benzene, this 1,4-benzene diboronic acid to result in the final compounds. These final compounds resulted in a good yield, and this is the structure. This is the structure, whatever the molecules we have synthesized. So we are having triphenyl as our pi linkers here, and at the end we have explored the tertiary butyl group, 4-methoxyphenyl group, 4-fluorophenyl group, and biphenyl group. So this is the absorption spectra of these compounds. We have obtained two peaks as so in the absorption spectra we are having our absorption band. This is a sharp band and this is a shoulder band which corresponds to pi to pi star transition, and the higher and the lower energy band corresponds to n to pi star transition here. So the emission spectra is also recorded, and we have calculated from their Stokes-Shift values as well. So with the so compound 3B here with 4-methoxyphenyl group, they have resulted higher Stokes-Shift and higher absorption coefficient values. Their cyclic voltammetric studies were also done, and in their cyclic voltograms, we have observed peak in both the positive as well as in negative potentials. So their onset reduction values, we have calculated LUMO energy levels, and from the onset oxidation values, we have calculated the HOMO energy levels. For these compounds, their LUMO energy levels are in the range of -3.40 to -3.97, and their HOMO energy levels were in the range of -5.26 to -5.89 electron volt. So these compounds are having band gap nearly equal to 3 electron volt. Their thermal analysis were also done, and these compounds were thermally stable with melting point higher than 203 degrees Celsius. So when compared to previous one, these compounds are more thermally stable. So for compound 4A and 4C here, we have observed a sharp endothermic peak, but for compound 4A and 4B, we have, in addition to endothermic peak, we have observed a glass phase transition temperature as well. This is a sum analysis of these compounds. Here the compound, first compound 4A result in flower-like morphology, compound 4B with 4-methoxy substrate. Although the packing is dense, but morphology is a bit different. So here the compound 4C with tertiary butyl group resulted in flower-like morphology, and this is the morphology of biphenyl substituted compounds. So their GIXT spectra were recorded, and peaks in their sharp peaks for compound 4B, 4C, and 4D. They are supporting their polycrystalline nature. So for these devices, for these compounds, their OFET devices were fabricated, and we have calculated their hole as well as electron mobility. Here, the 4-methoxyphenyl substituted compound exhibited only p-channel behavior, and the highest hole mobility was observed 2.5 centimeter square per volt per second with a current on-off ratio 10 raised to power 4 and a minimum threshold voltage of -11. And the maximum electron mobility here was observed for compound 3 with biphenyl as our end groups, where the electron mobility of 2.1 centimeter square 0.002 10 centimeter square per volt per second was observed with a current on-off ratio 10 raised to power 2 and a threshold voltage of 2.5. So this is the density distribution curves of this compound, and we can see that their pi-electron cloud is extensively delocalized for all of these molecules. This is the molecular packing from where we have calculated their hopping distance values. So to give an overall summary, with the extension in conjugation and introduction of linkers, we have seen that for these compounds, their melting point and decomposition temperature were increased. For when we started this compound 3A, they were having a melting point of 157 degrees, and the later it is having decomposition temperature of 319 degrees Celsius. We have also seen that their HOMO and LUMO energy level were increased. The interactive distances values were calculated. Their average grain size values were also calculated, and with increase in the conjugation, like from simple phenyl as end groups and to the 4-methoxyphenyl phenyl group. And also with this triphenyl group as a linker, we have seen increase in their whole mobility from 1 into 10 raised to power minus 4 to it is 2.5 centimeters square per centimeter square per volt per second. So it's a huge improvement. So I would like to thank Nagarajan sir for giving this opportunity to present among my
Okay,
peers.
Ansika, it's, you're done, completed?
Yes, sir.
Okay. John, now it's over to you, John.
Actually, we have an expert on organic field damage ancestors, so anyone can interact, they can start asking questions. Participants, the floor is open for discussion. No questions, I think everything is clear.
Hello, ma'am. I have a question.
Yeah.
Yeah.
In your morphological studies, there are different topological arrangements due to different substituents attached. Have you found
Yeah.
any correlation between the morphology and device performance?
Yeah.
Yeah, it is a bit hard to say. Like we do have observed, like we were thinking like we are having a very good arrangement, then the results were not according to that. So morphology does play a very significant role, but other factor like their homolumen energy levels and there are other things that is also equally important. But we can say like grain size does matter. Like when we are having a higher grain size, we have observed better performance.
Okay, ma'am.
Okay, Vinod, you may ask the question. Vinod, answer. Mr. Vinod, you may ask the question. Raise the hand. Okay, then I can ask one small question. Actually, once we do everything in lab, we are getting perfect result. When we fabricate device, what are the difficulties we may face?
So the main problem would be like what uniformity, like whatever we are, and the reproducibility. That thing is there. Like we have, we have. It's not like first, like we have done it repeatedly. Whatever the JXACT part pattern or whatever the PIXRT studies that we have done, we have repeatedly quoted the materials and recorded these data.
Okay, okay. Any other queries, sir? Anyone?
Yeah, Anshika.
Yeah.
Yes, sir.
It's a good work that you have done and a very good presentation. Most of your compounds, they have the methoxy substitution, right?
Yes, sir.
So any reason for that?
So actually, when we started, so these methoxy substituted compound, they were showing good results. So then we thought to just explore these compounds, this functionality.
Okay, so you mean in terms of electronic effects?
Electronic, and how they can tune the homolumen band, homolumen energy levels.
Okay, so
like when we are introducing this, triphenyl groups, so we really wanted to explore like how it affect with this with 4-methoxyphenyl group.
okay, fine. So maybe with an electron withdrawing group, you would have studied a different result would have been it would have been interesting.
Yes, sir.
Fine then. Thank you. I think, John, there are a few more questions in the message.
Yes, sir. Actually, I saw the question, sir. Ma'am, question is that why you choose the quinoline, sir? Any specific reason for that one? Quinoline.
Yeah, there is a big reason actually. When like the amount of research that has been done on p-type molecule is extensive. Like many molecules were explored when on p-type, and for n-type molecules there are less research was available. So when we were searching, we thought, okay, this quinoline is a new moiety and it was not much explored. That's why we decided to go with quinoline. Till now, I think not much that many reports are there.
Okay, then another question. If we replace the backbone with the quinoxylin or naphthalene, what kind of property we can expect?
So can you repeat the question? If we replace which group with naphthalene?
Yeah, the backbone with the naphthalene or quinoxylin, can we expect something improved?
I think then we can, then if we are introducing those group, we can expect these compounds to be more P channel, like they will act as a more P-type semiconductors.
Okay. Then another question. Okay, how can we calculate the mobility of charge carriers, or how to calculate it, mobility of charge carriers?
So this mobility, they were calculated from as I have told, like we are plotting two curves. We are plotting output curve and we are plotting transfer curve. So the carrier mobility here are plotted from the transfer curve. The formula is there. I haven't written it there here. So I'm very sorry for that part.
Yeah, no problem. I think we can wind up the session, Akshay. Any other questions, anyone? I think no.
So some more questions are there in the
Yeah,
chat
please
box.
read it. Please.
What will happen if you replace the backbone with quinoxylin or naphthalene?
Already asked. Okay, she already answered that question. Okay, ma'am, one more question. Why you have attached an acetylene linkage in the molecule design? Any specific reason?
Okay, the initially idea was that we want a planar molecule. So when we are having triple bond, it can make it more planar. Like it will obviously it will give the rigidity, or it will like rigidity will be there. It will be more planar. So just to idea was that it should be planar and like self assembly would have been better. So if we were using some double bond, maybe studies would have been different. But the idea to use triple bond was just to maintain that rigidity between the molecules.
Ma'am, one more question. You are getting different morphologies, okay?
Yeah.
Could you explain how different morphologies were obtained? Why it is given different morphology? I think that's a question from Rahul Kumar.
Yeah. So a different morphology. See, we have only. It was just like only with the simple substitution. Like we in some molecules we are having only tertiary butyl group, or we are having methoxy phenyl group, or simple phenyl group. With different end groups, this morphology was getting changed. So with just to explore, like we didn't expect that much variation, but yeah, when we did recorded the data that time, we have seen that huge variation was there.
Okay.
Obviously, these compound, when they are crystallizing, when they are solidifying, they are doing it in an exceptional way.
It looks Rahul is happy. In TJ curves, okay, I think a few more questions coming. Regarding the CV technique, are you using the drop casting method or the organic solvent method with the working electrode?
So for CV, like I didn't get the question.
One more time, repeat the question. In the CV technique, are you using drop casting method or organic solvent method with the working electrode?
So we have used this organic solvent method.
Yeah. Okay. One more question. So you have a rigid framework. What about the stability of this rigid molecular framework?
So for the yes sir. So for the first three parts, we got a good solubility, but for the fourth part, like when we are having that triphenyl groups, the solubility was a bit issue. But when we tried with different solvent, it was okay. We did try a mixture of solvents that time, so the solubility was fine. But it was not that readily soluble as in previous works, like the first three parts. I think those compounds they can be easily soluble in most of the organic solvent that are available in labs.
Okay, thank you, ma'am. I think there are no more questions, so we're very happy to have you, ma'am, and we got a lot of information from your talk. So on behalf of the Department of Chemistry and the ATAL FDP organizers, we thank you for your valuable time and
Thank you, sir.
Thank you.
Thank you, sir.
Chair, you may start next.
Okay, sir. So we have come to the end of our first session. The next session is handled by Mr. Ravikant Sharma, Director, Business Development, Impulse Technology. He has completed BTech with Electrical Engineering and he is working as the Director, Business Development, Impulse Technology. And also he is currently working on various EDA tools like Nano Academic and Flexim. He has conducted several webinars including optical and electrical modeling and simulation for organic semiconductor devices using SETFOS. Impulse Technology provide cutting technology of next generation nanoscale material and device, semiconductor devices, TCAD and quantum technology, simulation software for education, commercial and R&D sector in India. Over to you, sir. A very welcome to Organic Semiconductor Innovations, a faculty development initiative.
Yeah, okay. Thank you, ma'am. I'm audible?
Yes, sir. You are audible, sir.
Okay, thank you. First of all, I'm very thankful towards the ma'am and all of the team members and all the participants who joined these sessions. So first, I will be present a small presentation with PPT, and then we provide the live demonstration of the SETFOS tool. So my screen is visible?
It is coming, sir. It's coming.
Okay. So now it is visible?
Yes, sir. Perfect.
Okay, thank you for confirmation.
So please click that hide button, sir, so that we can remove that small message over there.
In the bottom.
In the middle. You just click that hide button.
Okay.
Hide.
Okay. So first, I would like to introduce myself. I am Ravikant Sharma, Director of Business Development from the Impulse Technology. So my Impulse Technology company that's provide the cutting technology of the next generation nanoscale materials and device, semiconductor device, TCAD and quantum technology, spin qubit quantum dot semiconductor device simulation software for the education, commercial and research and development sector in India. Our company also have partnership with Nano Academics, which is Canada-based company, and they offer several software like Nano Decals. It is used for device and material simulations, and Rescue, it is used for the material simulations, and one of the QTCAD that also used for the quantum device simulations, and Metra, which is a USA-based company that used for cloud-based material simulations, and one of the Flexim company, which is developed by Switzerland. So at here we will be discuss about the SETFOS softwares, which is developed by Flexim company. Our company also provide many of the services like software distributor, training program, technical supports, and equipment. like microprobe stations, solar cell, thin film, FET, gas sensors, transistor, resistors. For the more detail, you can check our company website impulsetechnology.in. Our company also have valuable customers like IIT Madras, IIT Guwahati, and IIT Dhanbad. Number of the valuable customers are uses the SetFast tools and equipments, so you can also take the reference throughout. So I'm here introduce about the Fluximagy company, which is Switzerland-based company that develops scientific tools that boost your research and development. It is developed generally simulation software for the upscaling for large area and measurement hardware of the OLED, perovskite solar cells, and OPV and electrical properties. It outcome of Institutes of Computational Physics in Zurich University of Applied Science. In 2006, Dr. B. Trussler founded that Fluximagy as a spin-off company. At here, number of the scientific tools that boost research and developments that developed by the Fluximagy. It is a SetFox. SetFox, it is a software for the organic perovskite solar cells and LED. And LEOS, it is a semiconductor software for the upscaling to large area device in OLED and solar cells. It also analyzes electrical losses in large area electrode. And one of the powers, which is an electrical characterization of the OLED and solar cell as used for transient photoluminescence and transient photocurrents. And one of the fellows, it is an angular luminous spectrum to characterize light emitting device, and simple word we can say dependent electroluminescence and photoluminescence spectrum measurements. One of the lighthouse, the generally used for the platform for the degradation analysis of the LED. It also used for the advanced LED stability measurements systems, and one of the lighthouse lights. It is a platform to perform parallel JV and stability measurement of the organic perovskite solar cell and perovskite silicon tandem polar cells. You can also check our company websites, Fluximagy company. So you can get more idea about the company. It's not opening like that. Okay, as we next move. So at here, I'm discussing about the SetFox, which is the semiconducting thin film optics simulation software. Simulation software for optical and electrical modeling of semiconducting device. It is a used for designing LED and solar cell based on organic semiconductor, perovskites, and quantum dots. Fitting and optimization algorithm also included in SetFox. Generally, fitting and optimization algorithms, that means SetFox generally give the high accuracy. So number of the times they simulate each nm calculation they can do. So that here fitting and optimization algorithm included. Operating system that use SetFox softwares which prefer to Windows 10. It's generally 64-bit version, Linux and Mac OS 11 also you can use. And next steps at the multi-threading ensure high-speed computations. Generally, it means SetFox parallel combinations as like parallel types of combinations occur. As we can say at the simple words, at one times number of the characteristics you can simulate at here. So as SetFox uses variety of model to simulate optoelectronics, including we can say every software tools generally prefer one of the models, so they can give the high accuracy. So SetFox also have the model that can use dipole emission models. It means predict the light emission characteristics of the OLED, and one second transfer matrix formation that calculate photon flux across the solar cells, and drift vision modules model charge transports and recombinations. One of the mice scatterings that optimize the concentration and refractive index of the particles that can be a scattering particles. So that four models that uses by the SetFox tools. So you can easily understand the SetFox follow the criteria which model we can use. So it can validate your projects. I am here for the live demonstration when we perform. So I'm considering one of the solar cell simulation examples. So solar cell, it is a semiconductor device which uses sunlight to produce electricity. A solar cell or photovoltaic cell is an electronic device that converts the energy of light directly into electricity by means of the photovoltaic effect. At here we will be simulates, we will be present how to optical solar cell calculation we can done and active layer thickness variation. At here that layer given aluminum P3HT PCBM as the active layer and PEDOT ITO. The similar layer structures we can consider at the SetFox because SetFox gives the availability of the layer and we can use at here unlimited layer structures. Second examples are considering at organic light emitting device. So an OLED, it is a solid state device consisting of thin carbon based semiconductor layer that emit light sorry, when electricity is applied by adjacent electrode. OLED are used to create digital display in a device and such as a television screens, computer monitors, and portable systems such as smartphones and handheld game consoles. So we can easily study about their characteristics at the single SetFox software because its GUI is too much simple. Two main family of the OLED at mentioned at here, those based on small molecules, those employ polymers. As here that one of the structures that given it generally means when we applied voltage across the OLED, electron from the cathode as the whole transport layers and anode move toward the emissive layers. When exciton pair are formed, so leading current through device, when the charge of the excitation path is combined at the emissive layer, so they will emit light. So the similar theory work on the SetFox, they follow the validity and what the theory says. So their results will be too much accurate accordingly. It is a graphical user interface. So at here that structures it is the graphical user interface of the SetFox. As you can see at here layer structures. So number of the layer structures I mentioned at here. It is a rough glass 1, rough glass 2, rough glass 3. So that similar structure I will create. So you can also use that layer structure, absorption settings and output settings, and you can provide your input at the geographical user interface. It is a device design and access to the device structure, material parameter, working file simulation outputs, and it also give easy access for the liberation of simulation examples. At here number of the examples are given, so mean at here that same. Multiple simulations can run in parallel, result automatically fastly generated that can be exported different format. This is a fully compatible with Python. At the script mode, you can also run your program. You can also give the inputs. So that means it is a fully compatible with Python. At the next step, as we move, SetFox model. SetFox generally have 4 different modules to simulate. Each module have unique feature to calculate various characteristics with higher accuracy. As here number of the modules given as absorption modules, drift division modules, so and emission modules, advanced optics modules. As the absorption modules when you activate, so modules that absorption of the sunlight or any spectrum by solar cells. So at the drift division, you can calculate all of the electrical behavior of the DC, transient or AC signal of OLED and solar cells. So means you can calculate all of the electrical parameters as like sine, wave, ramps. So you can give all of the parameters. So you can calculate it at here. So it is different modules. So emission modules, at here you calculate emission of light from the thin organic microcavities. At here, number of the emitted properties at you can calculate it at here. So similar at here, fourth module, it is a advanced optics modules used to design OLED and solar cell with scattering properties to enhance the outcoupling of light. So that four modules we can work at here, but also some of the toolbars given at here as like sieve parameters and optimization parameters and fit emission zone parameters. So you can also optimize your results, so can get better accuracy. First you can give all of the inputs as per your choice. As like absorption, if you want, you can activate. As you want distribution modules, you can activate. So similar, you can activate any of the modules. If you want to outcouple with these modules like absorption and distribution and absorption with emission, so you can also outcouple these modules. So my mean to say that Setfox are very easy and you can outcouple to each of these tools. So at here you can optimize, means you can get higher accuracy results as for the minimum and maximums your results. At the shift parameters, you can also multivariable can shift at the different ranges. At here some of the results that given result view of solar simulation. I have already run all those results projects. So the number of the results you can see at here. Absorption profile, energy flux at the 550 nms, generation profiles, and number of the results you can see at here, spectral absorption, layer absorption, and you can see at here the absorption profiles and layer absorption profiles. So each of the nms as the variation you can see at the left side. So Setfox as the give higher accuracy results at here. You can see at here number of the layer structure for the rough glass surface given at here. So I have already simulated that here result, but in the live demonstration I will show you how to put your data. Second, I'm choosing at the emission of OLED Setfox. So at here also given some of the results for the optimization modes. You can also calculate additional informations. You can see at here reflected, emitted, interesting. So it means the number which results you can see at here. So it will be so at here what will be emitted, what will be the reflected, and color diagrams, number of optical profiles you can see at here, exciton density, radiating dipole density, radiative riot profile, refractive index. So at here emission parameters are given, but this is a fit emission zone parameters. So you can see at here color diagrams. At the next steps, I will be move to the usage, design and optimizations. I have already told about the optimizations that for use kind of the performance of the solar cells, you can get better results. And Setfox also support impedance analysis and transient analysis. You can also validate your results, advanced research and development. You can also support your model for the mobile ionic charts. Setfox also include material property database. You can visual analysis you can also done at here. I'd like Setfox can simulate variety of properties including light emission, absorption, scattering, charge transport, short circuit current, open circuit voltage, and fill factor. Setfox support unlimited layer modeling for LED and solar cell and total absorptions and each layer specific layer and absorption. So graphical user interface, one of the best used for the, it is a too much easy structures. You can give all of the input at the single page with only single clicks and you can simulate your results because Setfox GUI is too much easy to use and multiple parameters you can simulate at here. Many of the software present in the markets, but I prefer to use at the Setfox because Setfox generally give the no limitation of the layer. You can give number of the layer, support transient simulations, all optical properties can be calculated, support mobile ion, cation and anion, support roughness and scattering particles. I will show that, compute the clear sky spectrum for given geographical location and time. It means if you want to calculate at the fixed time and the fixed location and fixed sky spectrums like geographical locations, India or any places of the states, so you can also give that parameters and you can get your results. Support parameters, SIP and optimization also includes a different range. Support hopping model for interface. You can also give at the interface layers and edge spectra. So I mentioned at here. SetFox can perform small signal analysis. SetFox is a commercial software with high regular update, user support, and training support. At the second side, one of the Escape 1D, it is a freely available tools. So if some software provide commercial, if considering some of the commercial software, so it have high chances to give the better results. And one of the Escape 1D, which does only support 7 layer, we can't support transient analysis, not possible to calculate all of the electrical optical properties, does not support ion and cations. At here, drift diffusion modules, you can give all of the cation and anions, hole mobility, electron mobility, so you can easily calculate it at here. SetFox generally does not support roughness and scattering. It does not support location and times dependent geographical model. It does not support shift and optimization. You can't shift at the fixed range or different range if you want. This does not support hopping models. If you want to do small signal analysis, you can't do done at here because it is a free. So generally, if someone thing is free, so it have the limited supports. At the next slide, I mentioned some of the application of the SetFox. SetFox is a simulation software used to models and optimize the design of the LED and solar cell and battery. It also used for the organic and inorganic solar cells, perovskites and tandem solar cells, heterojunction solar cell or thin film solar cells, dye-sensitized solar cell, organic photodetectors, quantum dot solar cell, organic light emitting device, perovskite LED, white OLED, tandem OLED, polymer LED blue, OLED, and hyperfluorescent, etc. SetFox have number of the customers are present as we provide many of the facilities as we have already told. We have the software distribution at big zones. So number of the customers users at the IIT Madras, Guwahati, Dhanbad, you can check out here. SetFox also give the validity of the research, number of the researchers doing their work on the SetFox and they validate their results. So you can use, if you click at here, you can check out here the multi-scales reverse bias broke down in all perovskite tandem photoscore model shading conditions. So that will be the reference phase, and SetFox also support these models. So you you can check out here number of the current density, reverse bias JV curves, and local 1D coupling loss connecting the 2D electrode. So multi-scale simulation approach. So you can validate your results at here. SetFox give the availability. It is a FlexiMagic company which provide number of the SetFox. You can easily study about the SetFox because each of the introduction, emission, absorption, drift diffusion, advanced optics, and references which are given at here. For the layers, similar given at here. All the features, modules for the Philos, Lightos, Light, and the number of the applications are given at here. Solar cell, OLED, photovoltaic tutorials, OLED tutorial, stability of the perovskite solar cells. So number of the researchers also do their work on that. So you can check out here the fluximagy.com easily. Number of the papers are given at here. As you can check out here, device simulation tools set first to perform cell level simulation and all perovskite tandem solar cells. At the diffusion simulation, mobile air consideration, coupling with quantum transport simulation, iterative analysis. So that provide the capability. And the laws also you can, for the large area, you can go with the laws softwares. It is some software to design and optimize large area semiconductor device. At here, 3 modules are given for the electrical modules, thermal modules, and 3D optics modules. Optical simulation with powerful 3D ray tracing algorithm. At here, the POS also given at the current voltage luminescence. You can check one by one each of the software tools so you can get easily understand what I want to say. So now I'm going with the live demonstration about the SetFox software. SetFox had the feature regularly updated. At here, new dropping models are introduced, so it will be tell about at here first page. The number of the SetFox features or version are available at here. You can check. So that is the SetFox toolbar. It is given at the up sides. It is a geographical user interface of the SetFox. So number of the examples you can see at here given. If you want to create your new simulation files, you can click at here. For the new simulation file, you can create at here. And for the existing results, you can save your results. If you provide current simulation at here, so you can save at here. Number of the existing results are given at here. So it is all of the SetFox toolbar. It is a passive optics modules. It is a absorption modules which are talking about. It is a drift diffusion modules. When you activate that module, you can calculate all of the electrical parameters. It is a emission zones with bulb-like symbols. For the scattering modules, if you want, you can activate that modules. At the master equations, it is a shift parameters and optimization modes for the better. And if you want your parameter extraction, so you can do it here. And it is a enable the emission zones. So fit feature of the emission calculation you can do and get your accurate results. It is a graphical input. It is a script mode. When you activate any modules, you can see at here. So all of the simulation and input are given at here. So now I'm going to simulate solar cells applications. So you can easily understand what I want to say. You can add unlimited layer through the plus I symbols. It is for the interface. If you want to add interface, you can click at here. So you can add it here. I'm here going to simulate solar cells. So I will put all of the layer structures that here. One by one, you can give each of the name. More layer you can add. P3HT PCBM. If you want to some deletes your layer, so you can click at here. You can delete also here. Now I I will be provide thickness at here. It totally depend on you which thickness you want. You can according go with your projects. So it doesn't necessary. I'm only taking example. If you want units change, so you can change that here. Discretization points also given at here. General tabs. If you want anyone to activate, so you can activate at here. Glass, it is incoherent considering, so I'm activated that tool. And discretizations for the discrete point, because set first calculate each of the nm calculation, so we did not want to calculate because it too much lengthy calculations and taking time, so I'm considering that here element 100. Which layers show the refractive index and wavelength dependent, so you can import at here .nk file formats. You can import ito.nk. You can see that here layer structures. If you changes your thickness according to their layer structures are changes. Similarly for the petard, you can import at here their files. P3HT PCM file also you can import. For the aluminum, similarly you can import one by one each of the refractive index files, but it is supported .nk file formats. You can see that here if any invalid structures are given, so you can see at the below sides. So set first also indicates about their invalid input. If you should be activate absorption modules, because we want to calculate absorption properties, so you need to activate that modules. Glass, you can also get the refractive index at here if you have not imported their files. Now you will be click at the absorption settings and you can see at here the shift parameters. You can also shift at here single wavelength for the shift, or wavelength or energy. So you can see at here from 380 to 780. Number of the steps you can considering. If you want calculate more number of steps, you can give at here your inputs. illumination spectrum files are already imported at here, but if you want to change any files, so you can click at here and import their file. It is a intensity scaling amount of the diffuse light. At the second simulation, I will show that amount of the diffuse light effects. Wavelength, you can change at here. Ranges, unit, it will be similar, so we can't change at here. Among all calculated quantities, set first quantified the maximum short circuit current if each layer present in structures and list. The high absorption value P3ST PCBM layer, that's material absorption, is designed to absorb most of the lights. So P3ST PCBM layer for the solar cell, considering at here, it is one of the active layers. Now you can give at name at here your simulation files. If you want abort your simulation in between, so you can abort simulation and give edit your value if you want, and otherwise you can run your simulation solar cell. So reflected properties are calculated at here, and you can see at here your results for the optical key frame, color index, reflected for trans glass, and the PEDOT, P3ST PCBM, short circuit currents, direct normal incidence power. So you can see at here your results, and absorption profiles you can also see at here, energy flux. So you can check one by one your results. White absorption profile, white spectrals. It is a layer absorption for the ITO. So you can click at here, PEDOT, you can click at here, and you can see at here layer your. If you want dotted, so you can click at here for the dotted dash. You can also mark circle, square. If you change your range at here, so you can change x-axis, y-axis, and you can zoom at here, plus and minus, and you can also see number of the features are given at here. If you want to hide some things, you can hide. If you want imports new, so you can import at here your items and your results. Properties, print, image, you can also save your image and data, select all the curves, you can copy. Now at here the simple solar simulation I'm done at here. But now if you want P3ST PCBM based solar cells under diffuse lights, so you can simply click at here, and but you need to activate absorption modules for scattering settings for the diffuse lights. So number of the angles you can give in at here, the diffuse at here haze specular aperture are given. That generally means the diffuse part of the light is then assumed to be Lombardian and the remaining part is specular. When reflected ray are scattered in different directions, so direction across the hemispheres. So you can change at here angles as per your choice, and you can run your results, but you need to activate the diffuse lights, and you can give at here 1 for the amount of the diffuse lights. you can check at a preview for the intensity at the y-axis and wavelength for the x-axis. Wavelength are also given at here. Similarly, now you can simulate your results again. If you want to give new names, you can give at here, and otherwise you can run your simulations. Similar at here, you can see in absorptions settings. Absorption graph are changed at here. Layer absorptions are also some of the effects you can see at here. And that parameters you can see at here. At the you can see at the similar layer structures, you can calculate absorption and scattering properties. But if you need with solar cell rough interfaces, so you can also go with this. So if you want rough interfaces for the solar cell, you can add number of the layers. Rough glass, one, rough glass 2, for the rough interfaces, as we are known to enhance the transmission of the light waves through the interface, we try to apply this concept because we decrease the reflectance at the outer air glass interface and to make the transmission from glass to ITO as advantage possible. So we use effective median approximations, and generally means it if some of the surface roughness that had a partial coherence and partial roughness. So effective median approximation we will be considering at here. You will be change thickness. It is an incoherence. So I'm considering at here. We does not more want discretizations. So only considering 5 elements. We also need to design at here porous ITO because for the rough interfaces is needed. So we can add one more layer for the porous ITO. So at here I mentioned the thickness as per demands. So now we need to the considering at here also effective median approximations file. So at here we will be choosing that EMA file formats. You can click at here for the imports your file. For the first you can considering at roughglass25.ema file. For the rough glass 2, similarly you can considering at here and imports that file 50.ema. You can import that file one by one. And for the porous audio, you can similarly import that file. Setfox also give the ability to export your own files at here. If you created your own files, you can also import throughout. You can give your own data. So you can create your own files and you can give the access to imports at here. So the number of the examples are given. So Setfox also have the major examples and major files that already presents. If you have no own file and the notepad, and you can import that here. So all the layer structures are completed at here. You can see at here. Top and bottom layers are semi-infinite mediums. So thickness are generally considering incoherent, irrelevant. So it is a rough interfaces. If you need deactivate that modules, you can deactivate. For the amount of diffuse light, you need only calculated for the rough interfaces. So all of the files are imported. If you want change any parameter, you can change. And if you want to give new run file, you can give, and you can again run your project. So at here rough glass interfaces, you can see the sum of the effect. You can see at the current for the P3HT PCBMs are increased. So rough interfaces increases the reflectance, and the profiles you can see at here, generation profiles, illumination spectrum files, wavelength for the real axis and the x-axis. I'm generally at here uses absorptions and scattering modules. Now if you want interfaces, so you can add interfaces at here, and for you need to activate spectrums, and you can also give at here. And if you want to you run your simulations, so you can easily run at here. So I hope at here you can understand the solar cell simulations parts. And now I'm going to considering one of the second example for the emission of the OLED organic light device simulations. So now I'm create at here new file for the OLED simulations. So similar you can considering one by one your file and take layer structures. Glass, ITO, dot, polymer, calcium, aluminum, you can change out here the thickness as well as I'm considering at here thickness 10 mm each of the. If you want change thickness, you can change as per your choice. Top and bottom layer are semi-infinite medium, so thickness are irrelevant at here. Setfox generally always calculate the emission spectra outcoupled through the top layer of the device structures. Which mediums, which layers are constant refractive index of the materials that do not show any dispersion. So we will not import it, but that mediums show the refractive index or which is wavelength dependent. So we need to import their file. And we know at here we will be imported .nk file formats. So you can check at here. Set Fox number of the you can see at here number of the files are given for the refractive index. So if you create your own files if you want, so you can also create. And at here you can see at here tabulated number of the file formats are given. So now I imported ITO.format. At here we did not want to import their files, so we mention at here refractive index only. For the polymers we imported at here pfo.nk file. Number of the files are given, so you can easily search out that files you want. At here pfa.nk files are given, so you can import that here. Calcium, if you did not want to import their files, it does not show any dispersion at here, so you can give at here only value. For the volume you need to import their file. You can see at here file not defined. If you set Fox also give the hints, if you some files not imported, you can check at here and you can understand what is mistakes you are doing. So all of the layer structures and refractive index files are imported at here. So that module you want to activate, you can do activates. So layer settings are completed. At the next step, the emission layer must be defined. So for the polymers, we need to activate the emission mode and absorption mode if you want. I'm activated at already the ranges are given at here. If you want change your ranges, you can change at here, but we did not want, so we can click at here. Define at here is undefined. So we need to define, we activate that emitter. So we need to activate file, and you can check at here wide, detail balance, Gaussian, Lorentz. That type of file you want to import, you can import, but at here I need ppv.pl file formats. You can see at here in refractive index.nk file format supported, but in the emission layer photoluminescence spectrum files are supported. So you can click at here photoluminescence spectrum files and you can import that here. If you want change or use units, you can change at here. You can check at here graphs and distributions. Number of the distributions are given at here: delta, exponential, Gaussian, excitant coupled, absorption coupled, recombination coupled. So that you can couple your modules at here if you want, and distributions you can given at here. You need to mention at here positions, dipole orientations. If you want isotropic, spiral, perpendicular, customs, you can give it here. Emission intensity, quantum efficiency, conversion efficiency, lifetimes, you can activate as per your choice. So if you want to activate that modules, so you need to couple that modules at here, but we does not want that modules couple, so you can simply deactivate that modules. So you can see at here ranges. If you want change emission modes, you can change for the mode analysis, dissipation, power analysis, spectrals. So spectral emission settings are also given at here. Filter, quenchings. If you want to activate that quenchings and the force resets, so you can activate it here. Now you can give the name of your results. At here, you need to activate power, probability, at here intensity at the x-axis and the wavelength at the x-axis and intensity at the y-axis. So that preview you want, you can also give it here. So now I will be give the name of the layer, but firstly we also consider it here which is emissive layers. It must be a transparent. So in the general traps, you activate the transparent set traps. Now you can give your simulation name.
This is for
Polymer OLED.
relax.
You can see at here your results, optical key figures and intensity. All of the results are given at here. Peak intensity, peak wavelengths, reflected and emitted and intrinsics are accurate here, so you can visualize your results through the color out. It is a color diagrams, exciton density, radiative dipole densities, absorptions, reflectance, transmittance, emissions you are calculated at here. So emissions zones are given. Normalized emissions are also given at here. So it is a script mode of the set fox. If any mistake you are done at here or forget to import your files, so you can check at here and you can also correct at here. But you need to check out. So the all of the input that you are given at here, you can see at here dipole orientation, dipole distributions. It is a console view where peak intensity, which time they are taken, what type of memory they are taken, used, number of the layers, all the symmetry, versions and operating systems. So all of the detailed information you can get at here. So it is a result view. So that parameters are calculated at here. So you can easily check your result at here. Now, if you want optimize their results, so you can easily optimize. But for the optimization settings, you need to local search, global plus local search, error and space and conf interval only. So different term you want to activate. If you want not too much lengthy calculations, not want accurate results, some a part of the results that you want, so according to you can choose at here. For the tandem solar cells, for the optimization you want, you can activate at here. You want that parameters optimize, you can choose at here. Simply you can click at here, opticals. You want optimize thickness of the polymers, so you can pre-scan or initial value you want to scan, so you can easily give at here numbers. Now at here you can see minimum value was not defined, so you can got your results. So you put their inputs. That ranges you can define at yourself. But we need to define at here target, because optimization settings want the target which, as we are as we are doing optimization of the thickness of the polymers. So if you want to optimization according to the radiations, dipole positions like that, so you can choose at here optical key figures, and otherwise you can simply choose at here. You can see it here, so you can easily choose that parameter you want target, so you can easily do. If you want to maximize minimum value, so you can set at here, and you can run your program. If you want to give names, you can give name, and otherwise you can optimize your results. So you can check at here the optimization results of the polymer thickness are given at here. Error function evolutions, parameter evolutions, key figures, what is the best to create results. So SetFox also give the ability to got your best results. Excitant density, radiating dipole density, as already seen at here for the emission. Now, if you want to fit the emission zone parameters, as here you want use that fit emission zone parameters, because we taken at here polymers for the emission zone. So you can also give for the accuracy of the polymers emission. So at here emission zone you can select at here and click at the right sides.
If I call now, my mom seriously, I'm sleeping call morning, not now.
Save visible data.
He will pick the call, but he will.
You can create your file name.
This year I saw some
Spectrum. At here you want to save a parameter file, material file, you can see it here. You can save that files. Now you need to activate that fit emission zones. So optimizations are deactivate already as per their choice. So emission spectrums you can unpolarized, yes polarized, p polarized. Now you can see that here your save files are given at here, and you can select that files and run your programs. You want give new names, you can give, and otherwise you can run your simulations. Kernel is status. 1 minute.
But in our place it is go till 7.
Yes, sir. Now they are still.
And I recorded
Network is हो गया 1 minute.
I didn't bought any blanket. Only that one small blanket. There, I went August. That time it was rainy season. That time I had 2 blankets. And now today morning, morning is not very long. This morning I woke up at 7 o'clock. Then I looked at
At here you can see at here I have already run the simulations. I think network issue due to regions. So you can
exactly 9:15 from.
check at here the same value that I have already input at here, and spectral modes and shift wavelengths and fit emission settings, and you can import at here their files. Similarly, at the output sheet for the sports result at the ASCI formats, and you can see at here your results. So it will be fit your emission parameters and the fitted dipole distributions, excitant distributions, recombinations, CI color diagrams, radiative rate profiles, refractive index.
Eight dosa.
For the emissions, it is a fit emission zones results,
Parota karna.
as it is a previous result that I've shown already.
Hello. Hello. Wait a dosa karna.
Setfox also give the warnings if some things that are missed out, so you can check out here and you can correct your value or inputs according to this color rendering index. I will show you for the perovskite solar cells some of the previous examples, as layer structures, absorption settings, and drift division settings, shift settings that tab are activated. So number of the parameter you can select according as like transient electricals for the electricals, layer, similarly electrode, top and bottoms. So you can shift your results according to the, you can linear, elements, element lock, random locks. So accordingly you can variate your results. At here layer structures are given for the air, glass, ITO, and the interface. If electrical interface are activated, so I've already told Setfox support hopping models, so you can enable at their hopping model for this interface, and the interface tracks you can also provide their inputs. So number of the at here two interfaces are mentioned, so you can check at here ITO, it is acted as like electrodes, and BCP also acted as electrode. So in between the electrodes need to be semiconducting layers. For the drift division settings will be on. At here number of the modes are given for the drift division settings. If you want steady states, transient for the hysterics and any parameters, AC, IMPS, IMVS. So you can accordingly click at that tabs. So it it is a perovskites voltage curves. If you want your parameters run, you can easily get your results. It is a saved examples because it's taking too much times. Built-in voltage, current balance for the voltage and current related graph. It is for the device current, power conversion efficiency, power density. For the electrical profile, you can check out here band diagrams, charge density, charge generations, current, electrical field, mobility, potentials, and recombinations. You can click one by one. You can see at here ranges. If you want to change your range, you can change at here Jacobian. Number of the formats results are given. Iterations, which iterations you are run. At here you can see current continuity, relative change, and number of the iterations. At the next, optical integrated photocurrents, all the stacked contribution photocurrents, number of the layer that included. passive optic properties, solar integrated absorptions, layer absorptions, reflectance, stack contributions, transmitted. So you can see at here number of the perovskites, LED, interface, emitted, emission settings are given at here. So SetFox also have number of the examples. If you want create your own projects, so you can take reference according to this, so it will be helpful towards you. And otherwise, if you have any query at here, so you can give SetFox also give provide the manuals and tutorial PDFs. So you can search your query, any things that you want. So 433 pages at given at here. So that tutorials one by one at given at here. So you can study at similar at manuals. All the theory parts are given at here. So you can also check at here. Full OLED, transients, strap contributions, that program I have already run, scatterings for the OLED. For the tandem OLED, you can see at here number of the layer structures are given at here, and two of the emitted layer will be activated at here. Tandem OPV opticals, tandem solar cells, that program I have already runs. Number of the interfaces are included at here. You can see at here. You can give the inputs value, absorption settings. It is on at here. If you want ship your parameters, you can choose at here incidence, wavelength according to this. So number of the example files are given at here. Set for Impulse Technology had own channel. You can go with this Impulse Technology. Number of the videos are given already at here. It is a SetFox cell simulations that currently made video. You can check at here all video as per your demand. It is a SetFox full playlist video. If you have any doubts according to their SetFox softwares, you can check at here. Number of the demo tasks are given at that video. For the laws, exabytes, key tickets, device studio, SAT equipments, risky softwares, all of the technology and GF and DFT formats that work on the content tickets. So Impulse Technology provide their information according. It is the latest video that made by the technical supports of the Impulse Technology, and that is the previous video for the set. As you can see in that video,
He has 2.8. That 7 has 3.3.
So you can understand what I want to say. If at the distribution settings, I need to also mention one things. If you activated the tabs, you can see it here in the general tabs. You can create your own electrical circuits and enable electrical settings. So for the steady state solver at the neat and gummels, for the number of the high convergence and dampings, iterations. If you want AC settings, you can amplitudes at like 0.01 at considering you can choose as per your demands. Frequency you can also sip at here. Current, sine and pulse wave if you want created. So you can easily create it at here and you can work on the at here ramp, sine, and you can give at here level and durations. So you can create your own sine wave like current waves graphs that you want. So similarly, set fox generally work for the semiconducting layer properties at the organic perovskite solar cells like that tandems, and you can use unlimited layers. So if you have any query about this set fox softwares, so you can ask about. And otherwise you can also check out here the tutorials and PDFs. So guys, if you have any query about this set fox tools, you can ask.
So now it's open for discussion. You can interact with the speaker.
Yes, sir.
So there is a question from Varadarajan. Is the thermal check available for maintaining the temperature? What is the maximum temperature it can reach and how it is controlled? Does it require liquid nitrogen or is water sufficient?
So if you want the range of the temperature according, so at here that mentions number of the files, so you can give the iterations. If you want temperature, so you can also give the temperature ranges. As need to mention at here temperatures ranges also given for the, if you can number different models have different ranges, and the drift vision settings you can check at here temperature ranges also given at here.
So basically, I would like to answer this query myself, Anil Sharma. Basically, this simulation software, you can apply some temperature and you can visualize the effect of temperature on your device characteristics. If you are talking about the experimental about liquid nitrogen, so we supply the probe stations. The speaker also introduced about micro probe stations. So micro probe station is basically vacuum compatible chamber, and it is multi probe probes is there, 2 probe, 4 probe is there, and liquid nitrogen will not be required because we also provide the water chiller for cooling the sample from minus 30 degree to 220 degree centigrade. The temperature controller will also be there. So the experimental facility we also provide and simulation software we also provide without needing of liquid nitrogen. So, Sahil, can you present this probe station slide?
Okay.
In your PPT also in second page, there are some probe stations image were also there.
Yeah, sir. Okay.
You can open that. So this back, yeah, this you can see this first one probe stations, vacuum compatible chamber. It is stainless steel made probe station, and 2 probe multi probe thin film solar cells characterization can be done. And we also provide the LED lamp. Light source will also be provided with the different color combination. Sample holder will also be there. And fourth one is water chiller. That is industrial water chiller. And it provides the cooling of sample without needing of liquid nitrogen. The sample can be cooled and you can characterize your sample from minus 30 to 220 degree centigrade. Even controller will also be there which can control your temperatures. Any other participant have any more query? You can free to ask, please. So is there any other query? Participant, please, if any query, you can ask directly. So OLED software can simulate different type of tandem solar cell, either CIGS, CDTE, even LED also. Multiple type of solar cell on different materials. You can use any material, organic or polymer or perovskite. It can simulate and calculate optical, electrical, and emissive, and DC, AC, transient simulations. All are possible.
Sir, one more question from Varadarajan.
Yeah.
OLED only suitable for polymer samples. Is it not possible for other materials?
So OLED is possible to simulate. Polymer is also possible to simulate in our software.
I would like to thank both the speakers for the day, Dr. Anshika Anjali and Mr. Sahil Verma. Thank you for your wonderful lectures and patiently answering all our questions. We are very grateful to have you here. And I kindly request all the participants to fill the feedback form and join the meeting tomorrow by 6 p.m. Thank you.
Thank you, sir. Thank you, Anil Sharma, sir. Thank you very much.
Thank you. Thank you to all.
Please, sir.
Thank you
Thank you
very much.